Hello students, in this video we'll discuss Gibbs phenomenon for convergence of Fourier series. Let's consider the function f of x, which is 1/2 pi minus x, defined for x between 0 and 2 pi, right? And so if we look at this graph, what do we see? The x-axis, the f(x)-axis. So at 0, we're at pi halves, like that, but it's open, and it goes down when you plug in x equals pi. We get to 0, so at pi it's equal to 0, and then it's open at 2 pi, right? So there's 2 pi. And so our function looks like this. And we do the odd periodic extension, extend this function to be odd and 2 pi periodic, as we typically do. Right? And so then what will happen over here, then we'll have a jump over here at negative pi, and then we're going to go down all the way over here to 0. And so we notice over here that this is negative pi over 2, this is pi over 2, and this is a jump of pi, right? So the jump over here is a jump of pi, okay? All right, and so there's a jump discontinuity. We know by Fourier convergence over here that this is going to converge to the midpoint, right? That's what the Fourier convergence theorem tells us. And so now, of course, what will the Fourier series look like? The Fourier series that approximate this, and so previously we calculated this. So since it's an odd function, the Fourier sine series has coefficients. The cosine coefficients are all 0 by odd, right? And so the b ends will be 1 over pi, the integral from 0 to pi. I'll put the 2 over, there's a 2 over there, so I'm just going to write like this. X minus pi sine nx dx. And these numbers are just 1 over n, okay? That's an easy calculation to do. And so in other words, this function f of x can be written as an infinite series. The sum n goes from 0 to infinity. Let's go say n goes from 1 to infinity, since we have sine series, right? And then I have a 1 over n, and then I have a sine of nx. So that's our full Fourier, this is our Fourier sine series. Fourier sine series. Okay. And so, of course, what's going to happen over here, if you plot the first couple partial sums over here, what you're going to see is you're going to see the Fourier series does this, 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 and then jumps up over here. And you plot this, and you start to see a phenomenon that starts to pop up, is that as around that jump discontinuity, there appears to be more of an overshoot than you expect, right? Things are pretty irregular around the points of smoothness, but at this jump discontinuity, even though there's a Fourier convergence converging over here to this value at the origin, I have an overshoot near the jump points. So we're going to examine that over here. So what we're going to do is let's consider Sn of x to be the sum. K goes from 1 up to n of 1 over k. The sine of kx, and we're going to let Cn be the first maximal point, that's first positive maximal point. So let's let Cn be the first positive point where Sn is maximized. Okay. So let's find out what that point is going to be. Let's do the derivative of Sn of x. So what's the derivative going to be? So Sn prime of x is just going to be, well, the k's are going to go away, right? We're going to have the sum. K goes from 1 up to n of the cosine of kx, like that. Beautiful. And of course, this relates to the Dirichlet. Of course, this is going to be the Dirichlet kernel minus a half up to a factor of 2. So this is going to be dn of x minus 1/2, where of course what's dn? It's just the Dirichlet kernel modulated by a half, right? So it's just going to be the sine of n plus 1/2 x over 2 the sine of x over 2. So I've just taken our Dirichlet kernel and modified by a factor of 2. So this is 1/2, it's 1/2 the Dirichlet kernel. Okay, great. And so, of course, if this is equal to 0, what can we say? So in other words, these points where it's equal to 0, if I set this equal to 0, this is true if and only if what happens? If and only if the sine, the 1/2s are going to cancel out, the sine of x over 2 is equal to the sine of n plus 1/2 x, right? And so one of two things happens over here, right? So the first thing that can happen in order for this to be true, the critical point, we analyze the critical points. The first thing that can happen is that x over 2 plus 2k pi can be equal to n plus 1/2 x. And the second case is that pi minus x over 2 plus 2k pi can be equal to n plus 1/2 x over here. All right, and so of course these first set of points correspond to what? Those correspond to x is equal to what? X is equal to the 1/2s are going to cancel out, so I have x times n is this, so 2k pi over n, right? So that's one collection of points. Or we can have these points over here. These points over here, I get an extra factor of pi, so I'm going to get 2k plus 1 pi over, now I have an n plus 1, right? So I have an n plus 1 in the denominator, right? And so it's easy to check by doing the second derivative test that these points over here are going to be points of what? These are the minimum local mins. These are the local mins. And these points over here are the local maxes. And that allows me to find out what this psi n is. So this, of course, runs from k going from where to where? K going from 0, 1, up to the floor of n over 2, right? Those are the values of k that we can choose for these points, right? And so in particular, this tells me what psi n is. So psi n has to be what? Psi n has to be pi over n plus 1. So this is going to be pi over n plus 1. That's my psi n. Now let's look at the partial sums over here at these points psi n, right? So in other words, if I can look at Sn of psi n, so I plug in the points of maximum, this is going to be what? This is going to be the sum, k goes from 1 up to n, of 1 over k, the sine of k pi over n plus 1, k pi over n plus 1, right? And now one sort of trick we can do over here, if I let the sum go up, k go from 1 to n, if instead I let the sum go from 1 up to n plus 1, the sine of pi is equal to 0. So I can put a plus 1 up here because I don't really change anything at all. And now we're going to do one tiny modification. What we're going to do is we're going to put a what? A pi over n plus 1 everywhere in the problem over here. So we're going to modify this a little bit, and how we're going to modify it, I'm going to turn this into a Riemann sum. And so the idea now is that I need to put a k over here, I need a pi over here, and then I need an n plus 1 over here. And so I'm going to divide by, if I do this, pi over n plus 1, that doesn't change anything, right? So I have an n plus 1 up top here, and n plus 1 those cancel, and a pi here and a pi here. And so now if we look at this carefully, what does this become? So in other words, this becomes the sum, let's erase that, we don't need that arrow over there, becomes the sum, k goes from 1 to n plus 1 of what? Of n plus 1 over k pi, the sine of k pi over n plus 1 times pi over n plus 1, right? And now as n goes to infinity, this turns into a Riemann sum, right? So in other words, the limit as n goes to infinity of Sn of Cn is going to be the integral from 0 to pi of the sine of x over x dx, okay? And now it turns out that what we're saying is that at the points of maximum, these partial sums are converging to this overshoot over here. And so in other words, you can actually numerically calculate this. And what this turns out to be is this turns out to basically be something like approximately 1.09 times pi. If you plug this into the calculator, you'll approximately get this value over here, right? And so that corresponds to what? That corresponds to a 9% overshoot, because it's 9% more of that overshoot of the actual jump size, right? Of jump size. And that 9% overshoot is known as Gibbs phenomena. So this is Gibbs phenomena. And actually, even though we only saw Gibbs phenomena for this particular example, for this particular function, it's actually true in this sort of a much more general sense. If I look at any function that has a jump discontinuity, I'm going to have the same sort of overshoot that occurs, even though I know that if it's just a simple jump discontinuity, the Fourier convergence will tell me that I'm going to converge to the point that's halfway between the jump points. But Gibbs phenomena always said there's always going to be near the points of maximum of the partial sums near that jump discontinuity, there's always going to be a 9% sort of overshoot or a miss, and it's exactly given by this integral of the sinc function between 0 and pi. Thank you very much.